Hey, hello. Before we start, do you have any question for me? Very well. So if you remember, last time we started by going through very simple classifier, linear classification. The fundamental approach is called Perceptron. We started with binary Perceptron, and we also looked at um, the algorithm that learns the weights for this binary perceptor. And if you remember, it was very simple. The approach was iterative. You start by an initialization of the weight equal to 0, and we select each data point, the training data point, one at a time, and then we calculate this W inner product between W and feature vector. And if it is positive, then the decision is basically the positive class. And if this inner product is negative, then the decision of the classifier is negative class. So it is binary classification. We have two classes represented by +1 and -1, very simple. And in this iteration, if the current weight for this particular example make the correct decision, and Y star represented the correct label for this particular example, then we do not need to make any changes to this W. But if for this particular example, the decision is incorrect, we need to adjust the weight, meaning that we need to change the weight, move toward the direction that next time, hopefully, there's no guarantee for this, but hopefully for this particular class, it makes the correct decision. And the update was basically adding the inner product between Y star, and Y star is either negative class or positive class to the feature vector for this particular example, and adding it to the current weight vector. So basically meaning that if for this particular feature vector, for this particular example, this weight do not produce the right label, we need to move that away from this feature vector in the feature space, right? We know that it is now the theta between these two is less than 90 degrees. So meaning that this has a bias toward this feature vector, we need to move it away from this feature vector toward this. And the way how we do it, basically, we subtract this feature vector from the current W, and next time this is the W prime, or basically the new weight vector for this binary classifier. So we make an update iteratively, example by example, to this weight vector, with the hope that after we go through all examples, after some iterations, basically the classifier makes no mistake for the training data. Obviously, there's no guarantee that it makes no mistake for the testing data, but we want to do that iteratively until it makes no mistake for training data. Any question about this? It's a very simple iterative approach. And this was an example. iteratively go through each example until it converges to the right weight vector that separate these two classes. Now we want to look at how we could extend it to multiple classes when we have more than two classes for this. For example, here we have three different classes, and we want to have a way to do the same or a very similar approach to update the weight vectors that does this classification for more than two classes. So it's very simple extension. For each class, we consider a weight vector associated to this class. So for example, when we have three classes, for each class, we consider a weight vector corresponding to that particular class, and similar the inner product between the weight vector for that particular class multiplying by the feature value, it produces the activation for that particular class. So for each particular class, now we have one activation value that determines basically how likely it is that the result of this classifier points to these particular classes. And then the way how it predicts, we want to, so basically for this, we have three different activation. For example, we could have Z1, which is W1 Fx, right? Z2, we have W2 Fx, and Z3, we have W3 Fx. Each of these basically are some values, some value, and then we select the classifier, select the label as a result that has the highest value of the activation, right? So it's simple comparison between these three numbers, and it produces the label by maximizing this activation. So it's very simple extension for multiple classes. Any question about this? So this is the way how multi-class classifier works, multi-class perceptron basically works. And if you want to visualize it, now we have such decision boundaries that separate out three different classes. And this decision boundary again is linear, right? For example, this part belong to class that we call 3, class number 3. This region points to the first class, and this region points to the second class. So this is the way how you could visualize it. Obviously, we are not assuming that these are clearly equal with respect to the space. It really depends on particle weight that has been learned. Some of the weights might be larger, some weights might be smaller, and the basically the size of each W determine the space that belong to this class. The larger this norm is, the larger the space is basically belonging to this particular class I. So it really depends on this particular norm of the weight.
Just a question, a
Yeah.
clarification, just to be clear, like that I understand what this method. So this is effectively just several binary classifiers, right? So each of them has their own weight vector, and if the values of the input, this f of x dotted with that weight vector for any given classifier is either like, you know, perpendicular or, you know, less, I guess, like into the negatives, then it's effectively just 0. And then we just say that like, it's not this classification. And then we look at the other classifiers, and then like we would check each of them and then just see like which of them is the largest value, right?
You could interpret it that way, but when we have multiple classes, right, when we have two classes, this separator is one line, is one hyperplane, right? And now for these three classes, we have three hyperplane. We do not have one hyperplane to separate these classes, right? So then for interpreting that way, you may want to consider, for example, when you have for this weight, you have this separator, then again, like it would be difficult to imagine it that way, because then this is for one class, and then we left with two other classes, right? So it is really difficult to interpret it with three different binary classifiers. But basically, it's better to think about this mathematically now, instead of thinking that this is really three binary classifier, because it is essentially not. We have three classes that basically for each class we have a weight vector that determine basically the size of this weight vector determine how large the space is for this particular class. That is distinguishable by these hyperplanes from the other two classes. And it is the same really with 4 classes, 5 classes. So instead of like thinking about like 4 classes is like 4 binary classification, because it is not, and it's not, I mean, it's maybe possible to imagine it some way, but think about like each particular class has a weight vector. It is a lot easier. And then we calculate this inner product between weight vector and feature value to calculate the activation for each. Does it make sense?
Yeah, thank you.
Any other questions? So again, how the learning works is very much similar. Nothing much sophisticated here. We start similarly to binary classifier. We start with an initial weights equal to 0, and then we pick up example one by one, training example, and then we predict the current weights. Basically, when we have an example, for this example, we have a correct label, right? We have the current weight vector associated to each particular class, and then we can calculate Zi, the activation for each class, and then we select Y as the output of this particular class that is associated to this example, the way how this classify with the current weight things. And then basically, for example, you can think about these are, this is the WY, this is WY prime, and this is WY star. Basically, Y star is is the correct label for this for this particular example, right? So if the decision is correct, obviously for this the decision is not correct, right? Because it points to y which is not equal to y star. So we need to make some adjustment in this case, and the way we do it, we really subtract, we do the same, the procedure is the same. We subtract this feature vector from this incorrect weight, right? So we make some adjustment with to the weight vector that was produced. So make sure that you understand this. So this is the label that was produced by the classifier, which was different from the correct label, okay? And this is the label, the third label, which was neither correct, neither considered as true by the classifier. So here we have three classes, right? Make sure you understand this. So we make adjustment to the label that, to the weight vector associated to the label or class that was incorrect. So we need to move that away from this feature vector by subtracting this feature vector from this correct. So this is the new weight vector associated. So this is the W prime Y. This is associated to label Y, which was incorrect for this particular example. And we need to make some adjustment toward this. How we need to do that? We need to turn that toward this feature vector. So we need to add this feature vector, right? And then move it toward this feature vector by updating W star, W Y star. So this is the update that we make to this feature, right? Does that make sense? Is that?
I'm sorry, I have one question if you don't mind me asking.
Yeah, go ahead.
So for our feature, which is a pink arrow, right? Is there a goal after like testing all the given data samples to get as close to Y star or to be exactly like Y star? Because I feel like if it matches up with Y star, it might be like overfitting.
That's a good question, but for this particular example, for this particular visualization, we are only talking about one example, right? We are talking about the update. The way how normal multi-class perceptron works, it doesn't have any clue rather than this update rule how to adjust this decision boundary in a way that it maximizes the likelihood of making correct decision for the test time. It doesn't have any clue. It has a simple update rule that updates the weights until it makes no mistake for all training example. And if such hyperplane, such three hyperplanes for three classes doesn't exist, then it doesn't converge at all. But assuming that it converges, it goes through all examples until it makes no mistakes for all examples. But it doesn't have any clue rather than this update how to make this adjustment the best possible way. But best, you might have some intuition, how does it look like? But it's not the case that it can find the a good, so like if these examples are given to you, you might like find good hyperplanes that is more likely to make correct decisions if you could visualize it in like maybe 2 or 3 dimensions. Even us, we cannot visualize it in more than 3 dimensions. But we could see it at least, okay, where to put these hyperplanes. This naive perceptron doesn't have any clue rather than this update. Does it make sense?
Yeah, actually that makes sense. I just realized that the Y star also, like in a real life example, right? Y star won't be defined for you, so it'll just naturally go in that direction.
Yes, yeah, exactly. So again, to clarify, this Y star is the correct label for this X, and X was this example in this iteration. The Y was the label that was predicted by the classifier, and in this example was not equal to Y star, so was the other class. And Y prime was the class that was neither true for this example, neither guessed by this classifier as a potentially true class, right? So it was the third class, and this is 3 classes that we have. Okay, in 4 classes, right, we have 2 of these kinds. In 5 classes, we have 3 of these kinds, right? So the classifier thinks 1 class, the correct label might be the other class, or might be the same. I hope this makes sense. So let's go through one example, right? This is the case where we have a multi-class perceptron, and we are given some sentences as input. So these are our x's, okay? These are inputs. And for each of these inputs, we have some correct label, and see what are these correct label are. So win the vote, and the classes are sport, politics, tech. Win the vote, like, is easy for us to identify. Win the vote, like, should be associated to politics, right? So politics is the Y star. So this is the Y star. Win the election, again, politics. Win the game, the sport. Okay, so these are the Y star. These are the current weight vector, and for each we can for each of these examples we can calculate f of x, right? How do we calculate this? We need to calculate the feature value associated to each individual features, right? So let's have this, let's calculate f of x for this first example. Obviously, we should expect that this f of x is a vector with the same size of the weight vector, same size, okay? You remember that from last lecture, the same size, because we want to calculate the inner product. We have a bias term, this is 1. Let's assume bias term is always 1. Win, how many win we have? 1. How many gain we have? 0. The first sentence. How many vote we have? 1. How many D we have? We have 1. Okay. And now the norm of this vector is 5, the same size of this. Let's assume that we don't have this, right? And this is the, again, f of x for the first example that we have. And when we do the inner product of with this vector, so is 1, the rest are 0, so it produces plus 1 for this weight vector. Okay, for this is all 0, so it would be 0. For tech is all 0, would be 0. So what is the label produced by this classifier with the current weight? Any guess?
Sports.
Sport. Is it correct or incorrect?
Definitely wrong.
Yeah, it's wrong because the correct label is politics, right? So it produces the sport, so it's incorrect. How we update this, and what is the correct label? This W, politics, right? How we update that?
We subtract the f of x from w politics.
Yeah. Do we need to do any adjustment to this sport?
So would you do the subtraction to the sports in addition to politics?
You tell me. So we should subtract from a sport or add to a sport?
I think we'd subtract from sport because we wanted to steer away from sports, and then we'd add to politics. So it's more likely to match it with politics when you do like the dot products.
Exactly. So so again, look at this. So y was the incorrect one, so we subtracted f of x from the incorrect label, and we added to the correct one. Okay, so we do the same. So this is incorrect. We subtract this from this. What is the updated version? So what is the w prime sport here? Is 0, is -1, is 0, -1, -1. And for this, it would be 1, 1, 0, 1, 1, right? Do we need to update this?
No, I don't think so.
Yeah, that's correct. We don't update the third class. We don't adjust the third class, right? So we adjust the incorrect label and the correct label, the weight vector of these two. And then we go through the next example. So what is the featured vector for this? Win, so bias is 1, win is 1, game is 0, vote is 0, D is 1. Okay. What weight I should consider? Obviously, this updated one. We ignore this, right? We use the latest weight. So when we do the inner product would be 0, -1, 0, 0, -1. This is -2, right? Did I calculate it correctly?
Yes.
Yep.
So for this is 1, 2, 3, right?
Yep.
And for this, obviously, 0, right?
Yep.
So for this, what was the correct label? Politics. What was the label that was produced by the current version of the classifier?
Politics.
Politics. Is it correct?
Yeah.
It's okay. Do we need to make any change?
Yeah. Should we reinforce?
No, I don't think we do anything.
No, we don't.
You know,
You don't update
you
anything.
don't adjust at all. Oh, okay. Okay.
Because it's good to go, right? For this example, it's good to go. For the other example, we don't know yet. But currently it's good to go, right?
Okay. So you only add. So when you get it wrong, you both add and subtract. And when you get it right, you just don't do anything. Okay.
When we get it right, like the
Why change it, right? If it ain't broke, don't fix it.
yeah, we don't need to. It's good enough. This is the way how it works. Like the only thing that the perceptron knows is so naive is just consider this update to the weight vector. Nothing beyond that. What's next? The third example, right? So let's calculate the feature vector for the third example. Win is bias is 1 again. Win is 1. Game is 0. Vote is 0. D is 1. Again, let's consider the inner product. It would be 0, -1, 0, 0, -2, right? Did I calculate it correctly? Was this calculated correctly?
I believe so.
Right. And this is again the activation, right? This is the activation value. This is the Z value. For this one, this would be 1, 2, 3, right? And for this one is 0. So what is the decision? The classifier thinks that this is politics, right?
Right.
But politics is not the correct answer. Sport is the correct answer, right? So how we do update here? The same as the first iteration, right? So we subtract from the incorrect label. The incorrect label in this class, in this case, is politics. So we need to subtract this. This is the current weight vector. We need to subtract this. Mm-hmm. Sorry that I made a mess here, but I hope that you can follow. So is 0 for the first, 0, 0, 1, right, 0. So this is the updated feature weight. And for this one, we need to add it up because this was the correct label, sport. So we want to add it, would be 0 here, 1 here, 0 here, 0 third, -1, and 0. Okay.
Yes. Does it matter the order in which you like the order in which the examples are? Is there like a specific reason?
That's a good question. Doesn't matter. For the perceptron, doesn't matter. We go over all examples iteratively to make sure that we can produce the correct label for all. So are we done here? Should we stop?
I was about to ask whether there was value of running again over the same examples.
Let's ask us, should we stop? The procedure was that we should go through all until we make sure that, like, for all, it produced the correct label. Do we know that it is correct for all? After we made the adjustment?
We might have broken one of the older ones by updating a newer one, right?
That's right. So we need to iterate again. We don't know yet. We may simply just broke even the correct ones after these updates. But let's check. Let's go back to the first one. The first one, this was the the feature vector, right? And the correct label was politics. With the sport, this is now the latest weight vector. So it would be 1, 0, 0, -1, 0. So it is 0. Okay. The activation is 0. For this one would be 0, 0, 0, 1, 0. So it would be 1. For this, again, this kit has not updated. So it thinks that it is politics, right? Is it correct?
Yep.
It is, right? So now it is correct. The second one, this is the, do we need to make any update? Obviously not, because like good to go. The second one is 1, 1. So again, here it would be 1, 0, 0, 0, 0. So it produces activation of 1, right? And for this one, it produces the activation. So we are considering this and this latest version, right? All 3 0, and then 0, and then 0. So I think the sport is the correct label, right? Did we calculate it correctly? Cody, did we calculate it correctly?
I'm having trouble following where on the which of the markings you're on.
Sorry. So this was the latest weight vectors, right? These green ones, and we are now pointing toward this. And this is the activation that was produced for this example. So apparently we are correct, and the decision is 1. The activation is 1, and the activation for the second class basically is 0, right? So it thinks that this is a sport for the second example, but obviously this is not a sport. So it's not making the correct decision. We need to make adjustment. How to make the adjustment? Similarly, we want to subtract from the correct labels. So we subtract from the correct labels. This one would be 0, would be -1, would be 0, would be -1, would be -1, right? I think we calculated correctly. I hope so. And for this third one, we do the same. We subtract W from this feature vector, would be -1, -1, 0, 1, -1. Okay, and no adjustment here. And then we go through the third example. Let's see whether this with this current weight vector make the correct decision for this. Again, for the activation would be 0. We are looking here. 0, -1, 0, 0, -1, -2 in total. For this one would be -1, -2, 0, 0, -3. Which one it selects? Selects the sport, right? Is it correct? It's correct, right? So for the third example, is correct. Are we done? No, we want to go ahead because we made one mistake, right? We made one mistake in this round. So we go again. until we make no mistake. For the first one, again, we are looking at here, and this is the latest feature vector, sorry, the weight vector. So it is, you should produce the politics. So 0, -1, 0, oops. So is 0, -1, 0, -2, -3. -3 for this, and for this would be -1, -2, 0, -1, -2. So it is a tie, right?
Yeah.
So what should we do?
Would we just update anyway? Like assume that we got one of them wrong and the other one right, and then just, you know, act as though we got it wrong?
Yeah, we could. So in this case, where there is a tie, and tie might happen, right? Because these activations are discrete. We could consider basically it is incorrect, and we update the labels, and we go yet another round to see whether it make the correct decision or not, right? So this is simple procedure, iterative procedure. And again, there is no guarantee that it converts. We may well go forever. We go until the classifier makes no mistake. There is no guarantee for convergence, and we stop when there is no update needed to be done. But very simple, right? It is simple procedure, easy to calculate things. The computation is very easy. Computation, dot product is always is not computationally heavy. So dot product is considered as one of those lightweight computations. Is there any question here?
Yeah, I have one tiny question. So like in real life examples, right? So in the example you just showed us on this PowerPoint slide, we were only able to get here because sports had a bias of 1, which allowed us to, like, you know, get at least some sort of 1 somewhere. Otherwise, if everything was just all zeros, it would always multiply out to be zeros and be even for all of them, right? No, do you, like, what I'm asking is, like, how do you get the initial values in the first place for real life examples?
So the initial value, if you are asking for these W, are all 0.
So if they're all 0, and then when we do the dot products, we get all zeros. So no matter what examples we
sorry. So basically, we have bias toward something, right? So typically we are dealing with one context, and that's why we have this bias term, right? Because we guess that most of these terms are about sport, could be about like politics, right? So we use bias for doing this, making this bias, right? So if we think that these sentences might be mostly politics, we make this 0 and we start this by 1, right? But these weights are all 0 initially. But we make the bias toward the class that we think might come from like our understanding or domain knowledge, what classes is more probable. Does it make sense?
Yeah, that answers it pretty directly. Thank you.
Sure. Any other question? So it's very simple. Let's go through what are some properties of these perceptrons. So basically, we discussed about whether these classes are separable or not, right? So in this case, we know that these two classes are linearly separable, right? Two or multiple classes are separable if the parameters get the training set perfectly correct, right? In this example, there exists such hyperplane that separate these two classes. In this case, it is not, it doesn't exist, right? At least not a hyperplane. There might be a kind of thing like this, or no, sorry, even worse. So it might be the case that, right, something like this exists, a decision boundary like this exists, but this is not a linear decision boundary. So for the linear decision boundary, such hyperplane doesn't exist. About convergence, basically, if training are separable, in binary case, only in binary case, it converges. There is guarantee about that. So there is proof that it converges. And actually, the number of mistakes, there is proof that there is a maximum number of mistakes if basically the two classes are separable, right? But even in multiple classes, such guarantee does not exist. Only in binary cases, there exists such proof. And the maximum mistake that binary perceptron in this iterative approach makes is basically upper bounded by this value. This is the K is the number of features. So it's the norm of W, right? And delta is the distance between these two classes, right? So the distance here is we are talking about this, right? Delta is basically distance between the maximum height distance between the hyperplanes that could separate these two sets, right? So when we push that way and when we push that way, how far away these two hyperplanes are, this distance determines how separable they are. So obviously it is tight. This upper bound is basically larger because it is difficult. So when two classes are closer to each other, it would be more difficult for any learning algorithm to find such hyperplane, right? So it is intuitive to make more mistakes, right? And that's why we have these cases. And K is basically number of features. Obviously, if number of features are higher, this number of mistakes would be larger intuitively because it needs more computation and it's more likely to get something wrong within this calculation. So this is some sense of like why this upper bound makes sense, right? But we can prove it if it's not difficult to prove this upper bound. But basically, it's upper bound on the number of mistakes within this iterative approach, right? So you remember like how many times we made this mistake or the algorithm made these mistakes. So we are talking about here, the number of features were like 1, 2, 3, 4, right? Or in general, like 5 with bias. So it was 5 divided by something that we don't know, right? Is basically the separation, the distance between these two hyperplane, something, right? So we can calculate this number of upper bound on the number of mistakes. Does it make sense? So let's have a break for 1 minute. We'll start in 1 minute. Okay, is there any question here? Very well, so let's continue. There are some problems with perceptrons. Obviously, it's not a perfect classifier or model. So obviously, one problem is that it cannot deal well with noises, especially if the data is not separable. You might trash a lot of weight, so you might iterate over and over again, and it may never converges. So that's a key issue. But more importantly is, as we discussed, there is no guarantee that it finds this separation hyperplane or the decision boundary. There's no guarantee that it gets it right? So if you are given this task, obviously without giving you the test data, you definitely prefer this hyperplane rather than the alternative ones. But Perceptron might well decide that this is the hyperplane that divides these two. I mean, there is no guarantee whether this one or it finds this one or that one, but it might well find this one and it stops there, because even this one gets all the example correctly, even though we know that it is not ideal. It's very close to one classes here, which is not ideal because we know that if we stay in between, there is more chance that this is a better decision boundary, at least based on the knowledge that we know about the training data. Okay. So that's one problem, but also there are other issues, especially like with overfitting as well, right? We know that I mean, we know that how we could think about overfitting. Typically, the way in machine learning we do things is that we have one test set, we have one held out data set, and we have the training set. Obviously, we want to increase our accuracy over the training data set as we go, but we do not want to go forever. We want to stop somewhere. This is basically a good place to stop. We don't know about the test, or at least if we have a test set, we should not look at it. But we can use held out data during our training. Basically, we do not use directly held out data for the training, but we could test how good the classifier is with respect to the held out data. And as soon as it goes down, this is basically this elbow point is the right way to stop, right? Obviously, if we go this way, it increases the accuracy over training set, but not necessarily over the held out data. So this is a sign of overfitting. We do not want to do that. So it's something that like we have a clue and we know how to do this early stopping. But more importantly, we want to find a way to address these two first issues. And actually, we have a way to address these two issues by improving, by extending Perceptron. Because if you think about this Perceptron, let's make a sense out of it, right? Perceptron use only knowledge with respect to activations. And activations are not probabilities, are values, right? So the extension over Perceptron, so basically you can think about Perceptron as non-probabilistic approach, right? It's not probabilistic model. Now we want to make them probabilistic because we might have better properties to reason about. Especially we can reason about with probability. We can reason about something like likelihood that give us some intuition or some measurable thing that we could favor this over this, right? With non-probabilistic approach, we cannot, because we only have like some crisp values. With probabilistic version, we do have, and that's the way we want to do it. So we want to make them fix them to make them probabilistic, and somehow we want to have some clue that, yeah, even though this is not the best linear boundary, but can we reason that, okay, it makes one mistake and one mistake is better than two mistakes? Can we somehow make a sense out of this by some probabilities? And yes, you can assign probabilities to each classes, right? So if you move toward this, basically you want to assign less probability for these red classes, more probability for blue classes, right? The other way around is vice versa. You want to make these red classes more probable than the blue class, and you have some sort of like probability over over two classes, at least within this case is two classes, right? So you can, instead of like giving that this is one, so you're talking about right, we're talking about one particular example, right? Instead of saying that this is the class, we want to say that this is 90% this class, 10% the other class, right? We want to have some probability distribution over two classes or multiple classes if we have multiple classes in the classifier, right? So we want to extend this crisp values 0, 1, and that was the way how Perceptron works, to some probability distribution over multiple classes. And we know that in order to have probability distribution, the sum over multiple classes should be 1, right? So you know this basic stuff. So you want, in a way, you want to turn these Z or activation values to some probabilities. How to do that? You have some clue, right? So you want to say that if this is very positive, you want maybe assign a probability closer to 1. If this is very negative, you want to assign probability to 0, right? So this is the way how you could think about this, right? In multi classes, we also will see that similar kind of transformation. So we need here a transformation function to turn this Z values, activation value, to some probability with the properties that we want. We obviously want to get the probability distribution, so we want to make sure that these two sum to 1, and we don't get any negative probability because we don't have any negative probability. So we want to have these properties, right? With activation, we had negative activation, right? We want, in probability distribution, we don't have any negative values, right? We have only positive probabilities. We have something closer to 0, even like having a 0 probability for some classes, it is weird, right? Because to some extent it is probable, but it is close to 0, right? But having 0 probability for one class is weird. Or having 1 is also 0, 1 is like the case for these normal perceptron, right? So we want to turn away from that. So in mathematics, we have sigmoid function that gives us this transformation. This is how it is represented. So if you go this way, or if you go to positive infinity, it will converge to 1, to minus infinity converges to 0. This is the mathematical representation. So this is the exponents, right? And this is the basically this is how it mathematically is defined, right? So sigmoid function gives this transformation. Obviously, there exists some other transformation function that gives this probability distribution or have some this kind of probability, but sigmoid is well used and is very popular, right? But make sure that you know that there exists such other transformation mathematically. And now we want to, since we have this transformation, we want to use some properties of these probability distribution to find the best W. And we now can think about best weight, right? Again, similarly to Perceptron, we want to find some W, but now we have a reason, we have a way to make sense and have some heuristic to reason about the best weight, right? And this is the way how you could get such best weight. So you want to maximize the likelihood of conditional probability of class label given the example. So this is the weights, right? So these weights are learned, and we want to learn it in a way to find the weights that maximizes this likelihood. Okay, so this is the output of the learning, and this is the way how you formulate it. So for all classes, you want to maximize the correct label. Yi is correct label, right? Again, in binary classification, we have Y0, Y1. 1 is correct label, or maybe you could represent it Y minus 1. Doesn't matter, right? You have two classes. Like 1 is correct, 1 is correct, 1 is not correct. So you want to maximize the probability, conditional probability that given the input and the weight, so these are given. You know the current weight, and you have selected a particular example, and this is for all xi. You want to maximize the probability of the true label given these input and the weights. So you want to find a set of weight or a weight vector to maximize this log probability, and this is the way how it works, right? So it's very simple. Again, you want to mathematically, and we know that this maximum likelihood estimation is a thing in mathematics. I'm sure in other courses you have encountered that. And this is different from like so this is the conditional probability, right? Make sure you don't make mistake with marginal probability. This is conditional probability conditioned on the input and the weights.
A question?
Yeah.
So you said that Y0 is like typically going to represent like a wrong answer. Y1 is going to be a right answer.
You can define it like however you want. It doesn't matter.
Right. But like in this particular example, you have xi as well, and x represents like all of the possible, what is it? Those are all of the training examples, all the inputs, I guess.
Yeah.
So if I have like, I guess it was just a notation thing, because I noticed that x has I and y has I. Right. So they have the same number of possibilities.
Right. Right.
Oh, okay. So this is because there's multiple classifications. So it's not just that you would have the example you gave with Y0 is, and Y0 and Y1, that's just a binary classification, but you could have multiple.
This is binary. So you have either class, positive class or negative class, right? So you have, like for each example, you have your probability distribution, your conditional probability distribution has two values. One, the probability of for the +1 class, one the probability for -1 class. So you have two classes, right? One positive, right? One negative. Sorry, one negative, right? So you want to find the weights that. So in this case, you might have this weight, right? So this could be your weight. And then for each classes, right? So for this, for example, you have a probability distribution that given this current weight, given this W, right? And given this X, this is particular X, right? Let's consider it X, I don't know, like X1, right? For X1, probability of, so you have a probability distribution where it consists of probability of +1 given X1 and W, right? And then, oops. And then you have, where is this thing? So you have here, come on. So you have basically probability of +1 given X1 and W is the current weight. So this is the current weight that we have, right? Assuming that we know W, assuming that we know X1, we have one probability and we have second probability, -1 given X1 and W. So these are the two conditional probability distribution for this particular example, X1, right? So obviously we want this conditional probability for +1, since this is plus, right? We want to be like maybe 0.95, right? And this one 0.05, right? So this means that this is much more probable that this the correct label is +1, right? And it is actually, we want to have this kind of case, right? Where it is more probable for one rather than the other. So it's discriminating one classes comparing to the other classes, right? This probability distribution obviously for this is different, right? For this, if this is X2, this P +1 given X2 and W, the same W might be, for this could be like 0.002, right? For probability of -1 given X2, W might be 0.998, right? Something like that. Does it make sense?
I believe so. I was having trouble for a moment reading what the formula really meant, but I think I get it.
Yeah, so basically it's very simple, right? So we have two probability distribution that basically showing what is the conditional probability given the weights and the for this particular example. It's very simple, and we want to maximize this likelihood, right? We want to go over all examples. We want to find the W that really maximizes this likelihood of these conditional probabilities. That's the way how you could think about it. Obviously, if you change W, each time you get different. If you calculate this likelihood, each time you would get different. And imagine that, like, you have many W, right? Like you have many W that you can think about, right? Let's assume that you have infinite compute and you go over all of these W, right? And calculate all of them, assuming that you have some infinite compute. And then you enumerate all of these and get the best. Obviously, this is not the way you want to do it, but this is one way you can make a sense out of it. Right? You go over all possible W because this is your variable. These are fixed, right? And you know that the correct label. So you know the correct label, and you want to maximize this likelihood. And this is called logistic regression, basically. So now you can reason, because now you know that for this you get one log likelihood, for this you get another log likelihood, which is totally different value, and you can favor this one over this one. So now you can reason. With the perceptron, you could not, right? So for both, you had the same procedure, and you could not distinguish these two, right? You could not really in Perceptron distinguish these two, because these two gave you the correct answer, and the way how you could end up in either of two was either by chance or by your initial value of the weights, right? You could either get either of these or something different, right? But you did not have any way to think or reason about like the best weights, or discriminate between these two different weights. But with probability distributions, with the conditional probability and log likelihood of this conditional probability, you can. So you can have preference over these probabilistic decisions, right? The same for multi-class logistic regression. You have multiple weight vectors, right? And now, so you have some weight over each classes. You have this Zi, and now previously with Perceptron, you got basically you calculated this weight vector, this activation, and then you selected the class label based on this maximization. But with probability, you want to do the same extension. Can we do that? Do we have any transformations like sigmoid? Yes. Here we have such transformation, which is basically called softmax activation. So I'm sure you have heard about softmax. We are now seeing some terminology close to neural networks. We are getting there. So basically, these are your original activation. These are basically the probability distribution. So like for 3 class, you have these 3 probabilities. Obviously, this is this a probability distribution? How we can say that this is a probability distribution? Can someone say why this is a probability distribution?
The 3 possibilities add up to 1.
Yeah, they have to add to 1. What else?
They're mutually exclusive. You can't, you're one of, or the other, or the other.
Yeah, this is the same, right?
Okay.
What other property we should expect from probability distribution? I just mentioned it for 2 classes. So obviously they should add to 1. So when we add them up, right? So it is easy 1 plus easy 2 plus easy 3 divided by easy 1, easy 2, easy 3, right? This is 1. So when we add them up, we get 1. So this is okay. The second property of probability distribution is common. It's very simple.
Can't be negative.
Yes, we should not have any negative. And we know that by definition, if we like exponent everything, this is the exponential function, right? So we do not have any negative values here, right? All positive, no matter what. Even if we go to infinity, it converges to 0, but it tends to all positive. It is no negative value, right? So this is property of easy if we have Z here, right? So if we go that way, it is going up very quickly. Let's go this way, it converges to 0 slowly. And it is nice transformation, softmax, because if we have Z1 larger than Z2, right, then EZ1 is a lot larger than EZ2. So this is a nice property we want to get, because we want to discriminate the true label. We do not want to mess up with labels. We typically want to have a discriminative classifier. So it prefers one class over the other classes, right? Unless the activation of these three classes is very close to each other, right? But most of the time we want to have like something like 0.9, 0.05, and 0.05, something like that. But we want one class to be a lot larger than the other two. And this transformation gives us that property, right? Typically, one activation is larger than the other two. And even if it is larger in a small amount, when we exponent that, the distance in the probability distribution become larger. So this has some nice property, and that's why it is it is common to have this. And then really we do the same. So we want to maximize the likelihood of this. We do the same procedure, the same naive procedure that we want to iterate over all weights to maximize this. Obviously, we don't have infinite compute, but for now, think that way. And this is called multiclass logistic regression. But for now, let's stop here, and then we'll talk next lecture how to do that in a proper way. So now we reviewed some classifier, perceptron and logistic regression for 2 classes and multiple classes. Next time we discuss about how to learn this, or how to do learning for this type of classifier, and also some variation of this classifier in a probabilistic way. So we discussed naive Bayes to give you an alternative of probabilistic model, rather than basically talking about going from input to feature weights and then producing the output. We discussed this part as well, right? Some probabilistic models to reason and make a sense out of it before we get to the neural network stuff, right? But it's I guess it's becoming we are getting close to neural network. But let's stop here. Talk to you on Thursday. Thanks.
Thank you.